Good morning. My name is Joe Morosco, and I'd like to have a conversation with you about making decisions and handling uncertainty. Decision making under uncertainty is a problem we all have every day. When we get to the fork in the road, we need to make a binary decision. Do we go left or do we go right? And what happens often is that people stop and wait for more information. They can't make a decision. And it's because they believe that the information that they have is either incomplete or uncertain. And this leads to what I might call paralysis by analysis. And it's pretty dangerous because while you're waiting at the fork in the road to get better information, you can get hit by a car coming from behind you. And the driver of that car is also probably waiting for better information. So paralysis by analysis is a situation we'd like to avoid. And the problem is compounded by our belief and the reality that new information is coming in all the time. While we're sitting at the fork in the road, it's as though the road was generating more branches. And, we'd have to analyze all those branches. So we are very, very much concerned about having a process that, when applied consistently, can help us make the best decisions possible given the information that we have. So the key to this is a process. And what we're going to do now is look for that process. And the only requirement is that you have an open mind and are willing to think logically. So let's try to define what are some of the ingredients or requirements that we'd like for our process. And there are three that I think are critical. The first one is that the process needs to be general. It needs to be usable for any problem. What we don't want to have is one process for making financial decisions and a different process for making medical decisions and yet another process for relationship decisions and so on and so forth. We would like an approach that is general in nature so that we don't have to have 14 processes. We can have just one very good one. The second requirement is that it needs to be evidence-based. In other words, whatever the process is, it needs to accept new information, tests, experiments, discoveries, and we need to use that evidence to update the confidence level in our prediction of how good our information is. The third thing is that the process needs to be practical, because if it's not practical, we won't use it. So we need to know the strength of the information that keeps coming in, and that will allow us to update our notion of probability to simple arithmetic. And you'll notice here I didn't use the dreaded M word, math, because we're not going to do math. We're going to do simple arithmetic that everyone is capable of doing. And when there is some arithmetic, I'm going to walk you through it. So have no fear about math. Now there's a second set of goals that are almost as important as the big three. We need to have a process that doesn't depend crucially on where you start out. And that's important because we have to be able to deal with the problem that I might believe that a certain statement is true, and you might have the notion that that statement is false. And we're going to explore what we mean by true and false in a couple of seconds. But the important thing is that we can't be stymied because two different people start out at two different places. We need to be able to start from any place. The second thing, or what I'm calling the second thing, but which is number 5 on the slide, is that we need to use all the data when we come up with our confidence. And that is, we need to use the old data that we have, and we need to update it based on the new information that's coming in. Recognizing, however, that all the new information coming in is not equal. Some tests are better than others. Some experiments are better than others. The new information could consist of a new discovery, which is very much at odds with our current beliefs. So we need to have a way of updating that takes into account the strength of the new information in the context of the old information. We want to use numbers to facilitate comparisons. And that's important because if I tell you that the Giants beat the Cubs today, that's information. But you might want more or better information. You might ask me, well, how badly did the Giants beat the Cubs? Because they're going to play again tomorrow, and I want to know, how to wager. And if I tell you that, well, the Giants beat the Cubs pretty badly, that's, one way of doing it. But if I tell you they beat them 13-2, that gives you a lot more information. 13-2, that's pretty crushing. If the Giants won only by 3-2, well, that's that was a lot closer. But it's the numbers that give us that feeling. So we want to use numbers, but numbers don't mean that we're going to necessarily use a lot of advanced math. We're going to use numbers that can be obtained using simple arithmetic. And then finally, we're going to apply this updating process iteratively over and over again. And that means that we have to make sure we don't have any infinite loops, because a process that doesn't converge is, in that category of paralysis by analysis. You can't keep going around the loop forever. You have to make a decision. Let's take a concrete, but perhaps somewhat outrageous example. What if Neil Armstrong had found cheese on the moon in 1969? That would have been very troubling. The whole world would have been pretty upset, I think, because existing theory, there was really no support for cheese on the moon, or the moon being made of cheese, or, cheese and moon were two words rarely found together in the same sentence. On the other hand, or as well, the prior evidence was all very indirect. Think about it. No one had ever been on the moon before. And it is kind of hard to argue with a piece of cheese in your hand. We would all admit that. So the question is, what would the scientific community have done? You might think there were two paths. They could have either accepted the cheese and said, well, everything we used to know about the moon and cheese was wrong. Or you might think they would just dismiss the cheese, saying, well, that's ridiculous, and one new little piece of cheese doesn't negate all of our prior beliefs or our prior evidence. And the fact is that they would have done neither. What the scientific community would have done was to modify their beliefs about cheese and the moon using all of the data, all the old stuff we had in hand and the new data. And it's that approach that's going to guide our thinking as far as our decision-making process is concerned. So what I'd like you to do is to change your thinking a little bit on what it means for statements to be true or false. We live in a binary world where we have to make decisions, but the information that underlies those decisions is not binary. In fact, if we look at things in the real world, most things are probabilistic. Their statements are likely true or likely false, somewhere in between. It's all about probabilities. We can't really ever be certain that something is either absolutely true or absolutely false. There's a very, very few statements that fall into that category. If we don't know anything, the probability that a statement is true is equal to the probability that it's false, which is 0.5, which means it's equally likely to be true or be false. And frankly, if we don't know anything, that's the most likely probability. But of course, people are not like that. People always believe they know something about any statement, and they'll assign internally or mentally a probability somewhere between 0, I'm sure it's false, and 1, I'm sure it's true. And that's what their current confidence level is. So what we're trying to do on this slide is move from this notion of true or false to probably true, probably false. And once people have assigned their probability estimate, what we then want to do is gather facts and refine that probability estimate. Thomas Bayes, who lived in the middle 1700s, invented a very powerful way of updating that initial estimate. He said, if I do a test and I get a positive result, the probability that that statement is true goes up. On the other hand, if I do a test or an experiment and I get a negative result back, that pushes the probability that the statement is true down. And that's just common sense. I mean, it's intuitive, right? But what Bayes adds to the mix is Bayes computes how much to move the probability up or down in each particular case. And the how much depends or ties back to the strength of the test that we just performed. We're now going to go through Bayes' updating process, which has 7 steps to it. The first step is the notion that it's an iterative process. If we've got a method of doing an update, we want to use it over and over again. And that leads to what I would call an iteration loop. And what we're going to see in this iteration loop is that we go around the loop multiple times. So every time we get a new piece of information, that's another pass through the loop. The new information that we get is used to update that prior probability estimate of the truth of a statement. So as a concrete example, Here our gentleman says, moon is made of cheese. That's not very likely. I'm gonna give that a probability of 1%, or in decimal numbers 0.01. And then we get a test. And here's the test in the moon case. Neil Armstrong finds cheese on the moon. That's new information. So how do we do the weighting of the new information? Well, the weighting is based on a couple of things. First of all, there is the strength of the test, indicated by the two muscles. And then there's the issue of the reliability. Where did the information come from, and is it trustworthy? And folding all that together, we come up with the pan balance, which does the weighting. It's got the old information, the new information, and on the upright here, a symbol that indicates that we use both the strength of the test and the reliability of the test in computing the weight. The result is something that is traditionally called the posterior probability, but we prefer to call it the updated probability, because the term updated probability is more evocative of what it is we're really doing. The Bayesian update step here has been purposely skipped over because we didn't want to clutter up this discussion of the fundamentals with a computation or a calculation. We're going to get to that in part 2. Don't fret about that. The updated probability becomes the new prior for the next turn through the loop. When the probability converges, and it will, the method asks us to stop and wait. And the reason for that is that doing additional weak tests is not going to change the probability much anymore. So we want to exit from what could potentially be an infinite loop. On the other hand, the possibility always exists that there'll be some dramatic new test or dramatic new data. And when that happens, we want to re-enter the loop and process that new data. So what it says is that we're never really done. We always have to stay open to new data and then analyze it even after we have aggressively stopped testing. So here we have all of the 7 steps on one slide alongside of the diagram of the method, and we want to point out that what Bayes really does is give us the computational apparatus to actually execute the scientific method, to take a numerical estimate of the probability that our statement or our theory is true, do an update, and get a second numerical estimate. So now we want to take a time out. We want to give you a chance to take a deep breath and perhaps go back and review If there are steps that still seem unclear to you, Bayesian reasoning is very powerful. It helps us reduce risk and crank down our fear of the unknown. It's enabling us to make the best of the information that we do have and to eliminate magical thinking. And even for people who have a little bit of math phobia, we're going to show you that it all can be done with simple arithmetic. So that's it for now, and we'll see you in part 2.